in Moscow, and it's 3:34 p.m. in Beijing. And I'm very happy to see Zsuzsanna, and she's now in Sydney. And she will tell us about a very important branch of mathematics. Actually, Dror is going to convince us that knot theory can be used wherever possible for solving algebraic problems. And Zsuzsanna will tell us about welded tangles and the Kashiwara-Vergne groups. Okay, so let's start.
Thank you, Vasily and Jayam, for inviting me. And there's not that many of us, so feel free to stop me anytime. I can answer questions. We can go on tangents. I'm happy for this to be a conversation. I'm going to be, at least I'm planning to be, telling you about welded tangles and the Kashiwara-Vergne group. And this is a bit of a survey talk, so I'll be talking about work of people many years before me, at least before my mathematical career. And also recent joint work with Eva Halacheva and Marcy Robertson, who are at Northeastern and Melbourne University. And this was just recently submitted to the arXiv, and that's the arXiv identifier. And also older joint work with Dror Bar-Natan, which was originally submitted in 2014, and now is a paper in Mathematische Annalen from 2017. What I'd like to start with is an obvious fact that you would have learned in your first abstract algebra course in your first year of university, or maybe if you went to high school in Russia, then your first year of high school, maybe in China as well. And it's the following. If you take a finitely presented algebraic structure, so this could be a group algebra, planar algebra, a wheeled prop. So I put some of these words here because these are the ones that will be relevant later in the talk, but this fact itself is extremely general. If it's finitely presented, that means that there are a finite number of generators and some finite number of relations. So I will denote the generators with G1 through GR and the relations with R1 through RS. And then let's say A is another algebraic structure of the same kind. So maybe we are talking about two algebras or two modules or two planar algebras. How do you find the homomorphism from K to A? This is a really basic question that I was just discussing with students in an office hour for second year linear algebra a couple days ago. To find a homomorphism, it's enough to set the values of each of the generators, because of course that will determine the value of Z on everything. But you cannot choose your values freely because they will have to satisfy some equations that come from the relations. So finding a homomorphism from K to A amounts to essentially solving these equations that come from the relations in the algebraic structure A. So there's a correspondence between two different kinds of questions, finding a homomorphism and solving a system of equations. And in the scenarios that I'll be showing you in this talk, K and Z will be some objects that are interesting in topology, and A and these equations will be objects that are interesting independently to algebraists. And this correspondence will give a bridge between these topological problems and the algebraic problems, which means that you can then use algebra, use your knowledge of algebra in topology, or maybe in a less traditional direction, you can use your knowledge of topology to apply it in algebra. That's the basic framework. Now, that's too general to be all that useful. So I'd like to firm it up by giving you a bit more of the technical details of this setup. So typically, K, which was our first object, that's some set of braids or tangles. So some sort of structure in knot theory. And an interesting fact is that many different structures in knot theory, such as the braid group is a group, tangles can be given a planar algebra structure. There's a category of parenthesized tangles. There are knotted trivalent graphs, which have a finitely presented algebraic structure of some weird kind. And what I'll be mostly talking about is welded tangles of various kinds, which have yet a different algebraic structure called the circuit algebra. All of these are finitely presented. What is not finitely presented is knots. So from this perspective, knots are just the wrong object to study, even though we are talking about knot theory. Knots are inherently transcendental. There are some operations that you can do with knots. For example, you can take connected sums, you can do cabling, but that's just not rich enough. There's not a finite number of knots that will generate everything using those operations. So anyway, let's say we choose one of the many right structures in knot theory to be the structure K, and then you can extend that structure by adding formal linear combinations. And this is, I'm being a bit loose, and I will be a bit loose in many points during this talk. So for example, if you take the braid group, then I wouldn't be allowing all linear combinations, only linear combinations between braids that reduce to the same permutation. So it would be the actual group algebra for the pure braid group, but if you take all braids, then it would be some restricted, some union of vector spaces. But that's a technical point that we don't need to get too stuck on. The important part is that we extend linearly, and then we also have some sort of multiplication operation, which in the case of braids would just be braid multiplication. But in the case of tangles, it's a more, it's a richer structure. You can compose tangles not just by stacking, but basically using any kind of linear connections. And then there are more exotic things like knotted trivalent graphs. So that gives some form of finitely presented algebraic structure. And then for the target space A, I want to choose a very specific thing, and that is the associated graded structure, degree completed. So let me explain what that means. Take this linearly extended algebra of some sort of knotted objects. In that, there's a subset called the augmentation ideal. The augmentation ideal is the set of linear combinations of knotted things. They're the coefficients sum to 0. In group theory, this is a sort of a basic object. This is an ideal in the most natural sense. So if you multiply something in I with anything in Fk, you would get something in I. And by taking powers of this augmentation ideal, you get a decreasing filtration on A. On K. I'll fix that really quick. You get a decreasing filtration. What does that mean? First of all, what does it mean to take powers of I? If I'm talking about, say, the pure braid group and the group algebra, then it's obvious. I'm just taking powers, just multiplying elements in I. But in all other cases, there would be some binary or multinary operation which I can use to compose. So for example, I would take a composition of linear combinations of tangles, 2 of which are in I, and maybe some others are not, then that would be an element of I squared. Then the associated graded space is the completed associated graded of Fk with respect to this decreasing filtration, which means, and again, this is a sort of standard algebra thing, which means that you take the direct product of quotients I to the n mod I to the n plus 1. When it's direct product, then this is degree completed. When it's direct sum, if it were direct sum, then it wouldn't be degree completed. Now, for my homomorphism, I don't just want any old map from K to A, but a map with some specific good properties. And if you're familiar with finite type invariants, the Kontsevich integral, this kind of side of knot theory, then this will not come as a surprise. This is basically what is called a universal finite type invariant. But there's another word that's more used on the group theory side, which is an expansion. And that's inspired by Taylor expansions. So an expansion from Fk to A is, first of all, a filtered homomorphism. There's a condition that it be group-like, but don't worry about it too much. That probably doesn't make sense at the moment because we haven't talked about any sort of Hopf algebra structure on A. And for the purpose of this talk, we can basically ignore it. But what is important is that there's a universality condition, and you can phrase this in sort of a very abstract way and also in a very concrete way. So the abstract way is just saying, because associated graded is a functor, the associated graded of this map Z is a map from A to A, because it's a map from the associated graded of Fk, which is by definition A, and to the associated graded of A, but A is already graded, so it's associated graded itself. So this is a map from A to itself, and we require this map to be the identity map. But we can make this much more concrete. This is simply saying that if I take an element X in Fk, then I can look at this filtration and find the last place, the last pair of I that contains X. So for example, X is in Fk, is in I squared, but is not in I cubed. Then its image would have to be the class of X in I squared mod I cubed plus higher degree terms. So the minimal degree part of the image of X would have to be in its class in the quotient where that makes sense. One of these, yeah, in the summand, which is
so do you use anything like Grobner basis or a Kirchhoff-Grobner theory for solving such equations?
No, not really. You'll see, yeah, there's some specific, for finding this creature, I'll give you some examples of what the methods are. It's not an obvious question how to find such an expansion, and it doesn't even exist in all interesting cases. But the basic point that we have seen so far is that then just applying this kind of obvious correspondence, very first year algebra correspondence, finding Z amounts to solving some equations in this debate. And solving equations in graded spaces have many interesting examples in algebra of sets of equations that people are independently interested in. So some examples are when K is what's called parenthesized braids, and I'll tell you about this in a second. This is a whole story from the late 90s. Then these equations are the famous pentagon and hexagon equations in the theory of quantum groups, and the expansions correspond to Drinfel'd associators.
By the way, excuse me, Zsuzsa, we have lots of pentagon and hexagon things in the study of our groups, G and K and gamma and K, and I think there is also quite a lot in cluster algebras. Do you work with cluster algebras?
I haven't, I'm vaguely aware of cluster algebras, but I haven't done any work in cluster algebra specifically. And I hope that you'll tell me more about the groups GK and gamma K. And
just join our discussions on Saturday or Sunday, or we can organize a separate discussion with you as you wish.
Yeah, unfortunately, Saturday and Sunday, I have a little kid, and so I can only work during work hours.
Okay.
So Saturday and Sunday, unfortunately, is not possible. Yeah, so, and then what will be the focus later on in this talk is this space of welded foams. This is a four-dimensional creature, kind of four-dimensional generalization of tangles. And that homomorphic or expansions, I keep saying homomorphic expansions because that's the term that Dror and I use. Homomorphic expansions for those lead to the Kashiwara-Vergne equations, which I'll tell you about also briefly. But I just want to mention that identifying these objects is not obvious. Figuring out, identifying A, of course, we have it identified, we have defined it, but there are combinatorial descriptions of A in each case, which makes it much easier to work with than something abstract like this. But finding that and proving that is indeed isomorphic to this associated graded space is not that obvious. And also, homomorphic expansions are not guaranteed to exist. And even if they exist, they can be hard to find. So for example, even though I said knots are not the right objects to study, but I just want to mention that the homomorphic expansion for knots is the Kontsevich integral, which is not a straightforward construction. Knots can still be fitted into this picture because instead of taking pairs of the augmentation ideal, you can kind of artificially construct that filtration, and then everything else after that works. All right, so before I go into these welded objects, I wanted to tell you a little bit about an old story. And this is basically from the late 90s, and many people have worked on it. And I just wrote down some of the most prominent names in alphabetical order: Dror Bar-Natan, Drinfel'd, Lam, Murakami, Tamarkin in the late 90s. And then also from there's an opera's point of view on this subject, and that's written down in great detail in a book of Benoit Fraisse from 2017. So in this case, the set of knotted objects, or the algebra of knotted objects, is parenthesized braids. These form a category or an operad, and on this slide, I'm just going to restrict ourselves to the category point of view because it's a bit more straightforward. So the objects in this category of parenthesized braids are parenthetizations of endpoints. So think of parenthesized braids as a combinatorial enrichment of braids. So the objects are parenthesizations, and then the morphisms are just n-strand braids. So you have, in terms of a picture, you have an n-strand braid just like here or here. And then at the bottom and the top, you have a parenthesization of the points, of the ends. And then you can combine all of these parenthesized braid categories by just taking their disjoint union. And this is finitely presented, generated by the crossing and the what is called the associator braid. So basically the braid itself is the trivial braid, but it goes from one parenthesization of 3 points to the other parenthesization of 3 points. And the operations here are composition in the category and also strand addition. So you can take a parenthesized braid and you can add an extra strand, which will be sort of an outside point. So it will be added to the outside of the parenthesization. Those are the generators. And it turns out that the relations are a pentagon relation and 2 hexagon relations. So the pentagon relation just involves all the reparenthetizations, like this pentagon of reparenthetizations of 4 points and no crossings. So it's only associator braids. And the hexagon relation involves both the associator braid and the crossing.
You see, usually people do not pay too much attention to the group part of the set of triangulations. But usually people just say that the set of triangulation of a polygon is as complex, and they study this complex. But you see, the groups gamma and k are just groups which appear when we study some actions on those complex. And I think from this point of view, gamma should be very much related to just associator part of the parameterized braid. So I think there will be associator part and there will be the braid part. So they both have to do quite a lot with gamma. Okay.
Yeah, I can certainly believe that.
And you know, whenever you ask combinatorialists who really want to study the set of triangulations or of something, they say quite a lot about topology, but they usually say almost nothing about group theory. And here we do have groups.
Yeah.
Okay.
So what's in terms of the if we are just turning this through the machine that I told you about in the full generality, you then have to think about the associated graded space of parenthesized braids, and that's turns out to be a space of parenthesized chord diagrams. Here, the objects are parenthesizations as before, and then morphisms consist of like a boring symmetric group part, along with an element of what's called the infinitesimal braid algebra. So this infinitesimal braid algebra is generated by these chords Tij, which diagrammatically we just draw as a little line connecting strand I to strand J. And this comes from, remember, this associated graded is a direct product of these quotients I to the n mod I to the n plus 1. And this guy lives in degree 1. So this would come from something in just I mod I squared. And I is the augmentation ideal. So the set of parenthesized braids where the sum or braid equals 0. And indeed, it comes from a difference of an overcrossing minus an undercrossing. So it somehow represents a crossing change of sorts. And you can see, in the difference, the sum of coefficients is of course 0. It's 1 minus 1. So then elements look like some stacking product of these chords, and then linear combinations of such things with some boring symmetric group part at the bottom or at the top if you wish. And there are a bunch of relations, and those relations are, well, Tij is the same as Tji because there's symmetry, and Tij and Tkl commutes when they are on completely separate pairs of strands. So for example, this chord would commute with this chord. And then there's this 4-term relation, which if you've seen it before, it makes sense. If you never played with it before, it perhaps doesn't say much to you, but either way, it's fine. It's not going to be central to the rest of the talk. So then you can make a whole space of parenthesized chord diagrams by just taking this joint union of all the chord diagrams on different numbers of strands. And an expansion is a map, a filtered homomorphism from PAB to parenthesized chord diagrams, which has this universality property. And in particular, the value, it's determined by the values on the generators, of which there are 2, the crossing and the associator braid. So the key to finding an expansion is finding an image for the crossing and an image for the associator braid. And Z of the crossing will essentially live in the exponential of the braid algebra on 2 strands, and Z of the associator braid lives in the exponential of the infinitesimal braid algebra on 3 strands. And these satisfy the equations coming from the pentagon and hexagon relations, which simply translate to the pentagon and hexagon equations which define Drinfel'd associators. So if you're familiar with Drinfel'd associators, then you know that they live in the exponential of T3. So basically, Z of the associator braid is a Drinfel'd associator. And this fact fits into a larger picture. Drinfel'd associators have some symmetry groups which have commuting free actions, left and right actions on Drinfel'd associators. And that has a very nice topological explanation in terms of these expansions. So if you take expansions from parenthesized braids to parenthesized chord diagrams, then the automorphism groups of parenthesized chord diagrams and parenthesized braids act on these on the right and the left with commuting actions. Technical detail is that here you need to do a pro-unipotent completion, but I don't want to go into that. And then these automorphism groups turn out to be isomorphic to these symmetry groups, which are called the Grothendieck-Teichmuller groups. So it all comes together as a complete topological framework for this algebra picture.
Can you give the corresponding definitions for Grothendieck-Teichmuller?
I would rather not. I can maybe at the end. So Okay, so associators are elements in X of T3, which satisfy the pentagon and the hexagon equations. And GRT1 is, just give me 1 second. So GRT1 is also a subset or subgroup of T or X of T3, and it is given by a also pentagon and hexagon equations with some permutations in the hexagon. But I don't, if you want me to write them down explicitly, I can, but it will take us a bit on a technical sidetrack. But maybe at the end, it would be a good idea.
Okay, I think there should be, so morally, G and K is more related to braids and gamma is more related to permutations. However, they both give us the invariance of braids. So we should investigate all of them all together.
Mm-hmm.
Okay, let's go on.
Yeah, so maybe one thing I can tell you is you're saying GRT is more more about permutations, and I agree with you. So these automorphisms are actually required to fix the chord. So they will only have they will only have interesting values on the associator braid, while here I think not much is known about what these automorphisms actually look like. So the way that you would prove this theorem, this is, well, several people did this in the category context. It was Dror's, and in the operad context, it's Tamarkin and Frass. So the way that you would prove this whole theorem, knowing this correspondence, is that you prove it on the graded side, because the graded side is much more tractable. And then you show that with this pro-unipotent completion in place, that isomorphism pulls through to the left side. And so this isomorphism on the left is more of an existence proof, and the isomorphism on the right is much more constructive. But I agree. This is more about purely the associator part, not much to do with the chords or equivalently the braiding. All right. So that's an old story, and the new story that I wanted to tell you about is kind of parallel to this, but studying a more complicated structure. So to get to that structure, I'd like to take a few steps. I'd like to start with welded braids because they are a bit easier to explain, and then we'll go to welded tangles and welded foams and the Kashiwara-Vergne equations. So you probably are familiar with the description of ordinary braids, so classical braids, as the configuration space of disjoint points in the plane. So similarly, the welded braid group can be described as the fundamental group of the configuration space of n disjoint horizontal circles in R3. when I say geometric circles, I mean these are not some crazy loops, they are actual circles, but their size is not fixed and they have to be horizontal. And just lining up those n circles in a row with I don't know, some given distance from each other and making them, say, unit circles.
Yes, you know, excuse me, for points on the plane and for braids, we usually look for some nice codimension 1 conditions, like 3 points are collinear, 4 points are on the same circle. And now I'm interested in the modular space of circles in R3. So we need some nice codimension 1 conditions. So if we have some nice codimension 1 conditions for sets of circles, then we will be able to start constructing G and K, gamma and K theory.
Well, so I'm not sure what I can give you as codimension 1 property. So in yeah, so I mean, when you say codimension 1, what I think of is where the braiding comes from, but this might be different than the sense in which you use the word. So for example, in R2, the braiding comes from 2 points coming around each other. And that is not, that's not null homotopic in R2. So in this representation of the welded braid group, the braiding doesn't come from 2 circles just swapping places around each other, because that would be null homotopic. R3 is too many dimensional.
Yes. But codimension 1 can work even in infinite dimension.
So here, where the braiding comes from is having 2 circles and one flies through another. So that's switching places movie, which is not null homotopic. So that's where the braiding comes from. But I'm not sure what to say about collinearity. 3 points collinear.
It need not be collinear. It can be whatever you want, but it should satisfy some axioms which are written explicitly. So on the plane, we can take, say, 4 points are coplanar, and there are many other situations when we have some submanifolds and so on.
Mm-hmm. Yeah, good question, but I'm not sure.
Okay.
So when you look at the configuration space, the fundamental group of the configuration space of these circles, what you're looking at is loops. So basically a movie that starts out with this configuration and then comes back to this configuration. And if you just stack the frames of that movie on top of each other, you get some tubes in R4. And these tubes, there's some braiding of these tubes, and that braiding has some special property, which is that you can fill the tubes to make solid tubes. Now, of course, while the original tubes were disjoint, so it's an embedding of tubes in R4 because we never had the circles intersecting. Once you fill them, those fillings might intersect, but the intersections have to have a special property, which is called the ribbon property, which says that all of the intersections has to be either the filling of some tube completely transversely intersecting the entire sort of circumference of another tube, or the intersection being completely in the interior of one of the tubes. So what's not allowed is, say, triple points or linking, where you'd have one tube intersecting another tube in this sort of linked way. Those are outlawed. That's the welded braid group. The welded braid group has a finite presentation, very similar to the Artem presentation of the ordinary braid group. And this is by a number of people in the 80s and up to the early 2000s. So I think the general statement is by Brendel and Hatcher from 2008, but building on work by other people. So the generators for the welded braid group there are two kinds of generators. One is similar looking than the generator for the ordinary braid group, and the other is these virtual braid crossings. And then that's up to some braid relations. So interestingly, while, I mean, maybe if you thought about this a little bit, then it's not so interesting, it's kind of obvious, but if you've never seen it before, then it can be a little confusing, that the ordinary crossing, which in ordinary braids means swapping places in this basic way, now means one circle flies through the other. And the virtual crossing, which doesn't exist for ordinary braids, means that the two circles just swap places. But if you think about it, this is how it has to be, just a sec. This is how it has to be, because there's no actual braiding with just swapping places. Yes.
Excuse me, if we have just, I think we can make the modular space finite dimensional if we consider ellipses, but can we realize it just by circles? So circles can change their radius, but if they stay circles, we can make the space finite dimensional with the same topology.
Yes, they can change their radius, and indeed they have to stay horizontal circles. So is the whole moduli space finite dimensional?
I think we can make it finite dimensional, and this will simplify things a lot.
Mm-hmm. Yeah.
Okay.
Yeah, I believe you. So so then in the algebraic presentation, the sigma i's, so the interesting crossings, which correspond to flying through movies, these generate an ordinary braid group. And the virtual crossings, which correspond to just swapping places in a null homotopic way, that generates a symmetric group, not too surprisingly. And the relations fall in several categories. So there's, of course, symmetric group relations for the virtual crossings. There's ordinary braid relations for the actual crossings. And then there are mixed relations, which are kind of the things, if you've done any virtual knot theory, this is what you would expect. And then there's an interesting relation called the overcrossings commute relation, which is saying basically that you can pull an overstrand from one side of a virtual crossing to the other side of a virtual crossing. And if you've never seen this before, I highly recommend acting this out with some actual circles. Like when I give talks in person, I sometimes bring along a few circles made of paper and just do the proof of this. It's kind of fun. And when you act this out as movies, you can really see why the two represent the same braid. So that's welded braids. The associated graded space of that is a welded version of chord diagrams, which are now arrow diagrams. So the chords become oriented. And the reason for that is because in the classical, say, parenthesized braids, the crossings corresponded to a swap of places, which is sort of a symmetric thing. But here, the crossings correspond to a fly-through movie, which is asymmetrical because one circle flies through the other. It's not interchangeable which is which. So we have oriented chords, which we call arrows, and the elements of the associated graded space looks like linear combinations of these arrow diagrams, modulo some relations which look a lot similar to the relations in the classical finite type invariance theory. So here an arrow encodes crossing minus a virtual crossing, and it's important that the arrow is pointing from the overstrand to the understrand. And when I say encodes, I mean this is a degree 1 element of the associated graded, so it corresponds to something in the augmentation ideal modulo the augmentation ideal spared, and this is that element in the augmentation ideal. The degree is given by the number of arrows, so this space, this diagrammatic space is graded. And there's a very simple homomorphic expansion, which is a bit surprising, because homomorphic expansion for parenthesized braids in the classical story corresponded to Drinfel'd associators, which is not a straightforward gadget. Here, the homomorphic expansion is simply sending the crossing, which is one of the generators, to an exponential of an arrow which goes from the strands which are involved in that crossing. And it's, I didn't write, but it sends all the virtual crossings to just empty arrow diagrams. So those don't participate in determining the value of the homomorphic expansion. So this is, you extend it so that it's so that it, commutes with stacking and with linear combinations, and you get something that satisfies the defining property of expansions, and it also separates welded braids. So it's a complete invariant of welded braids. This is in a paper of Dror and myself from 2016. So that's a bit of a surprise that this is so easy compared to the classical theory, which is rather complex. But in terms of getting some algebra out of it, it's not so useful because, basically there's a unique homomorphic expansion, and it's pretty simple. So no interesting graded space equations come out of this. But what if we look further? So we can study more complicated welded knotted objects, not just braids. The first one of those that comes to mind is tangles. I'll skip over knots and links because knots and links are just not friendly territory when we want things to be finitely presented. So let me take a short detour to talk about ordinary tangles. How do ordinary tangles form a finitely presented algebraic structure? The most elegant way that I know of is, I believe, due to Bar-Natan in one of his Covenant homology papers, to present tangles as a planar algebra. Planar algebra is a concept that was introduced by Von Jones. And it's basically a linear space where multiplication, and I say multiplication in quotation marks, multiplication operations are indexed by planar connection diagram. So a planar connection diagram looks like, let me white out the inside of these. So a planar connection diagram looks like a disk. Oh, that's too much writing out. Looks like a disk with some holes in it. And then there are some connecting arcs, maybe oriented, between points on the internal disks and points on the outside disk. And the way that such a thing acts on tangles is by, plugging in tangle diagrams so that the ends match up into the holes, and then the result is a bigger tangle. So every such connection diagram gives you some composition operation of tangles, and there are infinitely many of them. So this is an example of plugging into crossings to get kind of a braid drawn horizontally. Now, there's a generalization of these planar algebras, which is in this 2017 paper of Dror Bar-Natan and myself, and that's called a circuit algebra. So there, operations are again indexed by connection diagrams, but we drop the planarity requirement. So instead of an embedded one manifold, the connections are some abstract manifold. So basically just a perfect matching, a combinatorial thing on the endpoints that are marked on the input and output circles. So welded tangles are a circuit algebra generated by the overcrossing and the undercrossing, while classical tangles are a planar algebra generated by the overcrossing and the undercrossing. The advantage of this presentation, you could present this as a planar algebra, but then you'd have to add a whole bunch of virtual and mixed Reidemeister moves. You'd have to have the virtual crossing as a generator, and then you'd have to add a whole bunch of relations that basically just make that planar algebra into a circuit algebra. So the circuit algebra is an algebraic structure that makes the presentation of virtual and welded tangles more elegant and more concise. So the way it goes is that you take the overcrossing, take the undercrossing, combine them in all possible ways, not necessarily planar. So you could have these, what people call virtual crossings, appearing in the picture, just coming from the connection diagrams. And then the relations that you mod out by are just the usual Reidemeister relations and this overcrossings commute relation, which is the same as what we had for braids. I write R1F because I want frame stuff, but don't worry about it. A side comment is that in a paper that came out this year with Eva Halacheva and Marcy Robertson, I messed up the order of those names here. Eva should come first in the alphabet. We proved that a circuit algebra is equivalent to something that exists in operad theory called the Field prop. Now, for
没有人上课呢，有讨论班。
So please turn off your microphone. Please turn off your microphone unless you have questions. Okay, I think we should mute the microphone of of those who have no questions. Gian, please do it. Okay, let's proceed.
All right, great. So for welded braids, we had this Arden presentation theorem, but for welded tangles, that's not a theorem. It's only a conjecture that this combinatorial or algebraic presentation actually represents ribbon tangled tubes in R4. So tubes in R4 that are not necessarily ascending, but the same. And that's settled for braids, but open even for welded knots. The relations are, of course, true. It's easy to prove that all of those relations are satisfied by those topological objects, but it's not clear whether we have all of the relations. In other words, whether we have just a surjective map or a bijective map. And that's because of this ribbon structure that we don't really understand how ribbon changes are combinatorially described.
Okay, so I think there was some counterexample. I mean, there were different welded braids, or not, maybe different welded links, leading, which led to the same tube link. I don't remember.
Who is that by? Do you remember?
Well, I can find. I can try to find. I think it was in Singapore. So we will look. We will look at that 3 years ago. I saw an example. I will find the person who sent it to me.
Oh, I'd be very interested in seeing that because yeah. So I've been there's been some efforts by like Blake Winter, for example. He tried very hard to prove this theorem, and there are partial Reidemeister. There are Reidemeister results by the French group of people, Benjamin Audu, and I think Ballingary, Mailhen, various subsets of those people who prove Reidemeister theorems, but they assume the ribbon structure, so the fillings, as part of the data. And as far as I know, nobody has proven a solid Reidemeister theorem when that ribbon structure, where only the existence of it is assumed, not the actual ribbon structure picked as part of the data. So if there's a counterexample for links, I'd love to see it.
Yes, you know, one more question. So for virtual knots, there is a nice, there is a map which projects virtual to classical, so we can make some virtual crossings classical. I wonder whether anything similar can be done for projecting welded to classical.
Well, so virtual projects to welded by just introducing that overcrossings commute relation. So it's possible that your projection, that the projection that you're talking about factors through that, but I don't know.
Okay.
Do you know if it would?
No, that's the question. Okay, thank you.
Okay, so then for welded tangles, the expansion story is very similar to welded braids. There's a homomorphic expansion. Maybe before I say that, I'll note for ordinary tangles, there's no homomorphic expansion that respects tangle compositions. So in order to talk about expansions for tangles, you have to introduce these parenthetizations, and then you have the Kontsevich integral. But for welded tangles, it's actually very easy. So the associated graded there is arrow diagrams, all the same as for braids, except now arrows don't have to be horizontal. And it's the same construction for the expansion as for braids. So crossings just go to an exponential of an arrow, and virtual crossings go to nothing, go to empty arrow diagrams. It's very well behaved. It respects composition, tube doubling, orientation switches, tube deletions, pretty much any operation you can think of for tangles. Okay, great. But in terms of the algebra picture, so far all I've told you is that there are these welded analogs of various knotted objects where universal finite type invariants are trivial. So that's so far not very interesting. But then it gets interesting when we introduce just one more feature. And that feature is vertices and caps, but vertices are the real heart of the matter. So the next and last flavor of welded knot theory that I want to tell you about is called welded foams. So these are welded tangles which also have singular vertices and caps. So singular vertex, there's two kinds. And if you think of movies of flying circles, one of them is there's some circle that flies inside another circle and then they fuse and they become one circle, and that's how they fly on. And the other is when you have one circle and then it doubles itself, it becomes two concentric circles, and then one of them flies out and they fly apart. So I call one of those are kind of joke names that I only use for talks. I call this the marriage vertex and this the divorce vertex. And then we have caps, which is just capping off a tube. So in terms of the movie, it's a circle shrinking to a point and then disappear. Note that those vertices are not pairs of pants. So they are actually singular vertices. You have two tubes and then you glue them together at the end and then you glue a tube on top. Plus, we have to introduce more Reidemeister relations to describe how crossings interact with vertices and caps. And there are some extra operations, and the most interesting one is called unzip. So this is a tube doubling operation, where if you have a tube that connects two vertices, a marriage and a divorce, then you can unzip that, which just doubles that tube in the middle, and you get a picture like that. So that's an operation that says if you're going to marry and then later divorce, you may as well just hang out for the time being. Now, when I talk to people, there's often a lot of confusion about this being an operation. This is an operation, not a relation. So I'm not saying this picture and this picture are the same thing. They are not the same thing, but there's an operation going from this one to this one. So it's similar to like a tangle composition. You take two tangles, you compose them, you get another tangle. Here, you take a welded foam, you unzip it along a certain edge, you get a new welded foam. Then there's a finite presentation of these creatures, which is again as a circuit algebra, except now there are more generators because we have to include vertices and caps, and there's a bunch more relations. There are a bunch more relations which describe how those new features interact with the old features and with each other. And it turns out that expansions for welded foams do have an interesting theory and is deeply related to Lie theory. This is by Dror Bar-Natan and myself from, well, published in 2017, but done earlier. And the theorem is that homomorphic expansions for welded foams, which are circuit algebra homomorphisms and also commute with these other operations such as unzip, they correspond one-to-one to solutions to what is called the Kashiwara-Vergne equations. The Kashiwara-Vergne equations are a set of equations in Lie theory, and they have been around since the 1970s. The original formulation was more analytical in terms of convolutions on Lie groups. And the original motivation of Kashiwara-Vergne, as far as I know, was to prove the Duflo isomorphism. The Duflo isomorphism is a kind of structural theorem in Lie theory that says there's an isomorphism between the units of M of a Lie algebra and the symmetric algebra. Oh, sorry, the invariant part of the symmetric algebra. So this was first solved in full generality by Alekseev and Mencken, and I think that proof used deformation quantization. But then Alekseev-Enriquez-Torossian and later also Enriquez in the 2008-2010 came up with a completely algebraic way to solve these equations. And what they did was to construct solutions from Drinfel'd associators. And that's very interesting because Drinfel'd associators have a topological context, a topological equivalent in terms of homomorphic expansions for parenthesized braids, as I told you in the old story. But that can actually be modified to make something that looks a lot more like welded foams. When you have a parenthesization, you can close it up with a kind of binary tree. Let me draw an example just for fun. So say I have a parenthesized braid, and then I can close that up with a binary tree, making sure that I always connect the points that are parenthesized together. And what I get is something that has vertices and possibly crossings. This particular example doesn't have any crossings, but that's okay. Some other examples would. So that looks like something that could be interpreted as a welded foam. And indeed, expansions for knotted trivalent graphs can be constructed from the Kashiwara-Vergne integral and correspond one-to-one to Drinfel'd associators. And this is work of many people, initially Murakami and Otsuki and Chap-Tian-Le, then Bar-Natan, and I did this in a sort of bottom-up way in my PhD thesis. And then this construction of solutions to the Kashiwara-Vergne equations from Drinfel'd associators can be imitated in topology by building expansions for W foams directly from the Kashiwara-Vergne integral for knotted trivalent graphs. And that's something that Dror and I are writing up and should be done soon. So this is the picture just for expansions and the Kashiwara-Vergne equations. And now to put some substance in here, I'm afraid I'll have to tell you what the Kashiwara-Vergne equations are, or at least show you briefly. So there's, again, a very basic algebra fact that you would have seen in early university, if not before, is that if you have two non-commuting elements in some algebra, so the most basic example is matrices. If you have two matrices that don't commute, then if you multiply e to the a times e to the b, that's not the same as e to the a plus b. But there's a formula that tells you how to compute e to the a, e to the b, and I'll write the log of it. So e to the a, e to the b can be written as a single exponential. But I'll only write the exponent because it's easier. And that exponent is an infinite Lie series. So an infinite combination, linear combination of Lie-words in A and B. And it's called the Baker-Campbell-Hausdorff or BCH series in A and B. So the Kashiwara-Vergne equations, in some sense, improve on the Baker-Campbell-Hausdorff theorem. They refine the BCH series in some sense. So what are they? If you take the freely algebra on two generators X and Y and degree completed, so allow infinite linear combinations of Lie-words of increasing length, then we'll denote by T02 the group of automorphisms of the exponential, so the free associative algebra, which act on the two generators by conjugating by some given element. So it doesn't have to be an inner automorphism. It doesn't have to be conjugating everything by the same element. But when you act on the two generators, those have to go to some conjugate element. And the Kashiwara-Vergne equations are to find an element of this space T02, this automorphism group, such that it sends e to the x, e to the y to e to the x plus y, which are the participants in the BCH series, and some other technical condition. And I think given the time, I don't want to go into what this technical condition is, but there's some map called the Jacobian that sends these automorphisms to some cyclic words on two letters, and it satisfies a co-cycle condition and some other condition. It's uniquely determined, and you want the J of F to be of some particular form given by a power series. And this is the Alekseev-Enriquez-Torossian formulation. So the original Kashiwara-Vergne equations looked a little bit different, but this is equivalent. Now, how do these correspond to W foam expansions? So an expansion, again, is a map from W foams to its associated graded space. And that associated graded space is, just like for tangles, is some arrow diagram, linear combination of arrow diagram on W foam skeleta. So on pictures that look like W foams, but you flatten all the crossings. And is determined by the value of the crossing, the value of the vertex, and the value of the cap, because those are the generators. But it's subject to equations that come from the W foam relations. And then if you look at these specific values, the value of the crossing is actually uniquely determined. And it's the exponential of the arrow, just like for tangles and for braids. The value of the crossing is some arrow diagram on that skeleton, which is the crossing. And it turns out that the space T02 embeds in here. And the value of the cap is an arrow diagram on a cat strand. And it turns out that that's essentially a space of power series. So roughly, Z of the vertex will be the F, the solution F. Z of the cap will be the power series. And it turns out that the R4 relation, Reidemeister 4, which describes how a crossing interacts, or a strand, an understrand interacts with a vertex. You can pull an understrand under a vertex. That will imply the first KV equation, so this one. And some properties, basic properties of unzip, imply the second KV equation. So I just drew a picture of how this R4 implies the first KV equation. And I think if you're used to finite type invariant diagrammatic calculations, then this picture makes some sense. If you're not, then it will make no sense whatsoever. But that's all right. So basically, both T02 and the exponential of the Freely algebra on two generators embed in arrow diagrams on three strands when the generators X and Y are represented as an arrow from the first strand and the second strand, and elements of T02 are represented as arrow diagrams on the first two strands and act on this exponential by conjugation. And if you just write down what the, when you apply the homomorphic expansion, you just apply it to each feature. So there was a vertex and there was a crossing. So you get some value of the vertex and you get an exponential of the arrow. You do that for the other one, you get two exponentials because there's two crossings and the vertex. And then you do some arrow diagram magic and it rearranges to precisely what the first KV equation is. Actually, the action will be on the other side because what we'll get is not actually F, but F inverse, but that's technicality. So that's the heart of the matter. Of course, there are 1,000 other technical details.
Okay, thank you very much for a great talk. So do you still have something to tell us?
I have one last slide, and maybe I'll make this very short. So the recent work with Eva Halacheva and Marcy Robertson is completing that picture. So what I told you in the old story about associators. Here we had these Grothendieck-Teichmuller groups, and those were identified with automorphism groups. So in this case, again, there are automorphism groups which are called KV and KRV, and they're very analogous to the Grothendieck-Teichmuller groups. They have commuting free left and right transitive actions on Kashiwara-Vergne solutions. And we can prove that these can be identified with automorphisms of arrow diagrams and automorphisms of pro-unipotent completion of the pro-unipotent completion of W forms. And the way it works is that you do the graded side using exactly the same technique. You know, an automorphism here is determined by its values on the generators up to the relations, blah, blah, blah. So exactly the same framework. And then on this side, you have to do a pro-unipotent completion and show that homomorphic expansions extend to isomorphisms between this completion, circuit algebra isomorphisms between this completion and arrow diagrams. And then you can pull that isomorphism through to the other side to show the isomorphism between that group and automorphisms of completed foams. And interestingly, there is a conjecture, an open problem by Alekseev-Enriquez-Torossian. There's an embedding of the graded Grothendieck-Teichmuller group into the group KRV, which by our work translates to an embedding of the automorphism group of parenthesized chord diagrams to the automorphism group of arrow diagrams. And there's a conjecture by Alekseev-Torossian that this map is not only injective, but almost surjective. So they conjecture that the group KRV is isomorphic to the group GRT1 cross just a line. And well, it's an open problem, but possibly topology could help solve it, even though I've thought about it a little and so far have not gotten very far, but it's one possible avenue to attack that. And that's all I wanted to say.
Okay, thank you very much. I left some questions on the chat line. Maybe they are, and please ask further questions, remarks, comments.
I have a question.
Go, yeah.
Is there any spectral sequence that computes the completion?
Any spectral sequence that computes the completion? Not that I know of. I would love to be able to compute the completion. It's a bit of an untractable object to us at the moment. So all I know about that completion is via these isomorphisms, and that's not all that helpful, because computing the inverse of a like, if you take a homomorphic expansion and then induce to the completion and then want to take the inverse of that, I don't really know how to say anything intelligent about it. But if you have an idea for how to construct a spectral sequence for it, I would love to. I would love to hear.
Oh, thank you.
Okay, any further questions, remarks?
There's some things in the chat. Some of them are technical. How to write down? Yeah, I can't really answer the G and gamma questions.
Okay, any further questions? Okay, so let's thank Roger again. So just we can fix time to talk personally. I think that's more or less all. Thank you for a great talk. Hope to see you again sometime.
Thank you very much. That was fun.
Bye.
See you all.
See you.